Yeah, it's recording. Okay, 1 sec.
Let's go.
Okay, start whenever you want.
All right. Hello, everybody. Today we'll be presenting our project where we look into the basics of nuclear reactor design, and we try to make use of simplified reactor theory to demonstrate the process leading to the design of a critical nuclear assembly. And we try to show the crucial role of experimentation throughout the process by using MCNP.
So here are this is our original overview of our project. Our goals did eventually change, but we'll go through that as we go through. So first, we wanted to start with a homogeneous reactor because that's what we can most simply model, and that's what is modeled in the diffusion equation where we make that assumption. So we wanted to see how accurate is that actually to real life situations where it's not homogeneous. And then we wanted to split this fuel up to then compare it from this homogeneous situation to heterogeneous and how the criticality will be affected. And then split it up further and further so that it approaches the homogeneous case, but that part ends up changing as we go along. So this, we call it the idealist project as well, or the idealistic project, because the homogeneous, in our theory, we hypothesized that it would be the ideal reactor because, again, it's what we can simply model and reflect in our theory. And we assume that it would have the highest criticality, and then the rest will eventually approach the same criticality as it gets split up further and further. And then we will explain why we believe this with our findings.
Okay. So the first place we'd have to start, of course, is to make our homogeneous assembly critical. And so in principle, this shouldn't be too difficult. In fact, it should be really easy. You just define, a fuel to moderator ratio. I guess you can't really see it that well from here, but it is what it is. So this can just be your atomic density of uranium dioxide, which we take to be our fuel, and our atomic density of heavy water, which we take to be the moderator, and we take that to be that's just a weighted average, where eta and chi have to equal 1. So it's very simple. We can just play around with eta and chi. We can say, for example, okay, our atomic density will take 80% of our composition to be fuel. You can take 50% of it. You can take whatever number you want. You could play around with all those numbers in MCNP until you get something critical, so Kf equals 1. However, this method abates scientific excellence. You cannot guess your way into criticality in a realistic reactor design because you simply cannot afford all those resources. It would be impossible. So normally what you would start is with a theoretical approximation. The approximation will bring you somewhere close to where you want to be, and then based on that approximation, you make experimental measurements, which should be somewhere in the range of where you want to be. You're probably not going to be exactly there, but then you could fine-tune the measurement to get to where you want to. And once you fine-tune the measurement, you can cross-calibrate the theory. So in other words, you can bring the theory to match what is happening in real life, and then you have valid theory that you can use in your reactor design. So that's a very important process, which we're going to try to demonstrate with the simple homogeneous case. And so just to put into perspective that what we're doing is important, if you take the early years of nuclear research in Canada, in the World War II years, the Canadian English Research Group spent a lot of time cross-calibrating theory with experiments. So they had to perform a lot of experiments to calculate neutron cross-sections, so the group constants that appear in theory. So this could be fission, capture, scattering, many different ranges. The measuring of diffusion lengths of neutrons in various materials, so heavy water, graphite principally, and just lattice experiments in general to determine how well the theory fits. And so once you do this cross calibration of the theory, or the experiment to the theory, you will be able gradually develop with theory that is valid and to get more and more complicated and intricate reactor designs. And so that was the evolution, how in Canada we went from ZEEP, which was a zero energy experimental pile, first reactor critical in the world outside of the United States, from ZEEP to NRX, National Research Experimental, and then NRU, National Research Universal, and then finally from there, that was the basis for CANDU. So the theoretical approximation we're going to use, the one that we have with our knowledge, is the two-group diffusion equation. So it's very simple. There are many more reaction rates that could be included here, but we're not including all of them. So we're going to have to work with what we have. So the first equation is the one-group neutrons. So the neutrons that have an energy 1 electron volt or above. And then we have the two-group, which are the thermal neutrons, so 0.25 electron volts or below. So in the fast group, you have loss of neutrons from leakage, you have loss of neutrons from absorptions, and you have loss of neutrons from downscattering from the one group to the down group, so the moderation of the neutrons. But then you also gain neutrons through fission in the thermal group. The thermal group induces fission, the neutrons are born fast, so they land in the fast group. Whereas in the thermal group, you gain neutrons, so from the downscattering of the fast neutrons, you lose neutrons from the leakage, and you also lose neutrons from absorption, which is mainly fission and capture. And so we have all of these group constants, the macroscopic cross sections, which we're interested in. We want to try and approximate them as well as we can from a theoretical point of view, so we can get something close to critical for our homogeneous assembly. This is all for a homogeneous lattice, nothing more than homogeneous, which is why we're working that now. And so the group constants, so the macroscopic cross sections, you would be able to define them fundamentally as the microscopic cross section of the reaction times the atomic density, the number of nuclei per centimeter cubed, of the target that the neutrons are interacting with. And so typically you'll be able to find these from the database, from databases online. Many times you also have to average them, because especially in the one group where you're working with neutrons from ranges, 1 electron volt up to 2 mega electron volts, you'll have to average the energy. So it's not always easy. In fact, it's very difficult at times, especially for some of them. But the main idea is to properly configure the fuel to moderator ratio so that the reactor is critical at the smallest possible geometrical configuration. And so here is just a little more detail from the two-group equation. You'll be able to get your 6-factor multiplication factor, okay? You set it to 1 because you want your reactor to be critical, and then from there you get your material buckling. So if you have your material buckling, which is also the same numerically, the same thing as the geometrical buckling, you can solve for the dimensions of the reactor from there. But again, it's not easy, and this is where MCNP comes in as our so-called experiment.
So building off of that, for our MCNP procedure, now that we have the theory behind the first trial, we can run our first trial given that geometry that we found for the like what atomic fraction we need for the minimum geometry, because we don't want an outrageously large reactor. So first we used those dimensions. We didn't actually reach criticality as expected. We had to vary the atomic fraction a little bit until we reached that, and we found that it saturated at about 0.86 as opposed to 1. So we just added the reflector that gave us that extra bit of reactivity, which brought us to critical. And then we broke up this simulation, broke up the fuel and the moderator to make the heterogeneous simulation. So this is still homogeneous. For our first homogeneous run, we used the 5% fuel to moderator ratio, which was found as the ideal ratio based on theory. That gave us in our experimental trials, which is our MCNP, that actually gave 0.71, which seems very off, but that's still a much better first assumption or first iteration than if we had just randomly come up with arbitrarily like 80%, for example. So then we knew though that given it's still 0.71, we'd have to lower our atomic fraction by quite a bit, which is what we did. And this is what you can see here. So we ran quite a few trials here to get this distribution, showing that we get our criticality of about 1 at 0.2% of the fuel. So it's very small compared to the 5% even that we found in theory. And we also see that if the atomic fraction is too low, the criticality isn't going to be high enough, which we would expect because there's not enough fuel. But then if it's too high as well, there's too much U-238 absorption in the U-238. And this obviously was done at, may not be obvious, but it was done at constant volume to keep all other factors the same. And then continuing with the homogeneous exploration, we decided we wanted to also look at how volume would be affected. So we increased volume from 9, or the radius, because the radius and the height are equal, so we increased the radius and the height from 9 meters to 15, and that is very large, but that is just the reactor that we decided to design. And our red line here shows the highest criticalities, which is at 0.2%, as we found previously. That's the optimal one, but you do see how if it's 0.25, so if it's higher than that, the criticalities are still generally lower, and then the same for 0.15% is even lower.
And so here we just did our cross-calibration with the theory. So the main cross-section that we were not that well convinced about was the downscattering cross-section. We couldn't really find any proper cross-sections for that, and the only way to do that is experimentally. So when we ran MCNP and we saw that we were getting a lower K value than we should have, we looked at just the downscattering cross-section, and we found that had to be much lower. And we'll talk a bit why that might have actually been the case. Why in a homogeneous reactor, more neutrons are getting lost in resonance captures and are not making it down to the thermal group. But we'll talk about that in a bit.
Right. So what we ended up doing with these two assemblies that we have, a homogeneous and a heterogeneous reactor design, we wanted to look at some of the parameters just to try to verify if our theoretical assumptions and hypotheticals are accurate or not. So to do that, we tried to measure the surface flux out of the moderator in both the cases, as well as the fission rate and the energy deposition into the moderator. What we found was that the surface flux outside the moderator, or out of the moderator, it's much lower in the homogeneous case it's much lower in the heterogeneous case compared to the homogeneous, 2 orders of magnitude lower. And that is in line with our hypothetical as well, that a homogeneous reactor with fuel present everywhere is more susceptible to leakage on the boundaries, while our heterogeneous design had a single fuel rod at the center. We also verified the fission rate because that was our main assumption going into this model, was the homogeneous reactors would be very conducive to fission because of the presence of fuel material present everywhere inside the moderator. And we found evidence to support that theory. We found that the fission rate in the homogeneous case was twice as high than the heterogeneous case. But this number could be somewhat misleading, and as we think through this, we believe it could possibly be a fuel pen just not receiving all the neutrons present in the moderator, and leakage and the resonance captures, all of those playing part, which we'll get into. And ultimately, the energy deposition was interesting to look into, as we found that the homogeneous case, yes, it had a higher energy deposition in megaelectron volts per gram of the moderator into the moderator from the fuel, while the heterogeneous case had a much lower value. The challenge would be, how do you extract this extra heat from the moderator? But that's something that the homogeneous reactor excels at. Next, please.
So overall, our findings, this is coming back to the homogeneous case, we found that the atomic fraction is very important for criticality. As we said before, too much and there's too much absorption, and too little and there's just not enough fissionable material. and then the volume also will change the criticality, which makes sense based off of the curvature. As you can see here, as the radius increases, the flux at the boundary surface decreases. So with higher radius or higher volume, there would be less leakage at the boundaries, which is why one of our theories for why there's higher criticality. And then continuing here for comparing the homogeneous to heterogeneous again, here are two figures to represent what we're talking about here, but this is heterogeneous, homogeneous. So here we can see that our biggest theory for why the heterogeneous is less critical than the homogeneous is because here in heterogeneous you can see that it's much more likely for either the neutrons to get absorbed in the fuel bundle because it's such a large area of fuel, and there's definitely going to be paths throughout that bundle will be absorbed, or a lot of them might leave the fuel bundle and then just not come interact with another fuel pin, so then it'll just leave. The only instance where the fission would occur is if it was reflected back or somehow scattered through the moderator back to fission, whereas here every bit of fuel is essentially almost guaranteed to go through a moderator. So it's basically guaranteed to be moderated, but the factor to consider here is that even though it's going to be moderated, it may not be thermalized. So here it is thermalized, causing fission, but for example here, it's thermalized just enough to reach resonance energy, and then it will be captured. So that's what we would see more resonance capture here. And then of course there's still leakage on the boundary, which we saw because there's more fuel in general near the boundary. And then other factors affecting this as well are with heterogeneous, usually you have cladding or some sort of shielding around the fuel bundle, and we do not have that, and we don't have less.
So what we basically tried to work on throughout our project, if we can go back to the idealistic overview, the idea was to start with a simple homogeneous reactor to understand what's happening in that one as much as we can, and then from there to make the reactor fully heterogeneous, so to completely separate the fuel and the moderator and to see what sort of things happen. How should we expect the criticality to be different? That was more just for us to understand what's happening from a theoretical point of view. We can't expect to have something like this to be critical in any case. In fact, the criticality, the reactivity was actually lower than in the homogeneous case, because there we don't have any lattice. So as was mentioned before, the neutrons that come in here, they basically, a lot of them are just dispersed outwards, and they don't have any other bundles in the lattice. So it goes out of there. In a normal reactor, you'd have, neutrons coming out from one fuel bundle, and then it would land into another one that's spaced appropriately according to the diffusion length. And so that's how you normally model a critical lattice. But given that we don't have the theoretical basis to design a critical lattice, that would require transport theory, that would require a lot of numerical analysis, and it gets very complex. We can't do that, so that would be something we would consider as a follow-up. For now, we did our simple homogeneous case. We demonstrated that we can cross-calibrate the theory and the experiment. We were able to go through that basic process in a very simple case, but we were able to demonstrate that process. And so yes, pretty much the next step for us would be to keep separating the fuel into smaller and smaller elements, and as we do it, to upscale the theory, so to use transport theory, and to keep this cross-calibration going between the theory and the experiment. So you have theoretical assumption of a lattice, you make that lattice, you test it, you see the results, and then you keep on doing these fine-tunings until you get your critical reactor. But for our purposes, we started with the very simple, just to demonstrate that it can be done, and this remains to be seen. Yeah, that's our presentation. Thank you.
Thank you.